Well, I'd like to thank the conveners for letting me have an opportunity to talk to you at the end today. I guess I should probably bring this up to full screen so you don't see all the silly things I have on my computer. So I'm going to come at this from a little bit different point of view. I've come from this from a data end, started off looking at ionospheric data 15, 20 years ago, and slowly build up tomographic imaging techniques, and then build up to imaging and data assimilation. And I'm going to skip a lot of the other heavy things people talked about and try to just touch on some of the things and try to get us out of here on time. And you might start by asking that question, why would we do this? I mean, it's kind of been answered, but this is an important question to ask. Why bother with ionospheric imaging or data assimilation? Which I use those back and forth, but they're not exactly the same, but a lot of the techniques are similar. So I'm going to first address that question, then I'm going to talk about inverse theory a little bit, and then ionospheric tomography. Inverse theory, because really, that's what this is. And in fact, a lot of us in this field use inverse theory all the time in one way or another. So it's not a bad idea to get a little bit of a sense of what that is. Ionospheric tomography is a nice, simple inverse theory problem you can get your hands around. Then I'm going to talk about the current state, 3D global imaging of ionospheric electron density and other things, and their time evolving, and where we're going with that. Show you some science we've done with it that we think we can continue doing with it, and then talk about some of the next steps as we go forward, which has been mentioned here three times. You probably want to get down to estimating the things that are hard for us to measure. Winds, electric fields, temperatures everywhere. Those are some of the things we want to try to get to. Well, why do we want to do this? Well, it's no surprise that the thermosphere is a complicated, complex, coupled system. But we don't always think about what that exactly means. I mean, to me, this is a really exciting and difficult system to get our heads around. I mean, we have external forcing coming from the sun, and we don't know that forcing all the time unless we have upstream measurements of it a little bit, and we don't have complete measurements of it. And as we've started to talk about in CEDAR, where these systems and coupled, the ionospheric-thermosphere system is coupled to the magnetosphere at high latitudes. It's coupled to the mesosphere and the stratosphere from below. You have gravity wave fluxes, planetary wave fluxes. So it's a coupled system. It's got external forcing. It's, of course, nonlinear. It's got multiple species that you have to track of ions and electrons, but it's sitting in a neutral fluid, which is actually the denser part of it, and changes with altitude, this neutral fluid does, and it has its own winds and temperatures. So you have to deal with all those things simultaneously. And then just to top it off, because we like to make things hard, we add Maxwell's equations to the mix, and we have to know about currents and electric and magnetic fields. So it's difficult. Not easy for us to accurately model it, even theoretically understand it, predict it, or interpret what we see in the world. So you start saying, well, what can we do? And some of the things we can do is we can use imaging and data assimilation to actually specify from data, observe structures in the ionosphere and thermosphere, follow them in time, and maybe get a better understanding of them. As people have talked about in getting at the drivers, we might be able to use all these measurements to get estimates of state variables that are difficult to measure, at least difficult to measure everywhere. I mean, neutral winds, you can't measure them in the day very much. They're at 1 or 2 altitudes, very difficult. And by doing that with data simulations, we can then help just observationally understand the environment and the system we live in, but also, as was just talked about, maybe find ways to understand what the limitations in the modeling is and how we can improve it. Well, what are some of the things that can be done or have been done with data assimilation imaging? Tons of ionization, highlighted polar patches, boundary blobs, that's been done. Storm-enhanced densities. Anthony Acosta really led the field on that. Now everyone looks at images of storm-enhanced density and see how they evolve in time. Others are starting to look at sharp gradients, my colleague Sabani Dadabaru, and their effects on systems like WAS. Equatorial anomalies and the plumes. You want to take some of the large-scale gradients and maybe estimating conductances you can get from electron densities equatorial to provide inputs to electrical spread F predictions. People do traveling ionospheric disturbances. I'll just let you see them all. There's a lot of things that data assimilation techniques can do to help understand the system we live in and maybe make progress in our overall scientific understanding. So those are kind of the motivations. Okay, so this is what we all learned in our physics with calculus courses, forward predictive theory. Start with a forward predictive theory, say force equals ma, for example. That's a forward model. You know, you've got your acceleration and your force, and you can predict forward what's going to go on. And in general, we're taught that all the coefficients are known and the theory's exact. And so basically, if you start off with your known initial conditions, the position and the velocity, then you can predict where the ballistic trajectory of the particle or whatever goes, everything else. That's a forward model, and we can compare with observations, and that's fun. I wish we could do it, because then it's a lot easier. You just get to see how these things time evolve and move on. Inverse theory is a little different, and it's what most of us do. We start with some observations of the system that we've made from our instruments, or we've downloaded observations from the internet or from satellites or whatever, and we take what we know about models or theory that relates to the observations in some way, some mathematical way, and maybe we have parameters of the model that are unknown and unknown initial conditions, and we apply some type of mathematical estimation technique to go from the observations to some better understanding of the model, its parameters, or its initial conditions. And that's inverse theory. And there's a lot of issues with inverse theory just in general, no matter how you apply it. You almost always have incomplete data or errors on the data. I mean, there is a branch of inverse theory that's exact if your data was exact. You generally don't know the model, we just saw, or you don't know all the parameters in the model, or it's missing things. So that leads to non-unique solutions and potentially large errors on solutions. General rule of thumb, if you have error x and you go inverse, it's like going 1 over x, the inverse errors are big. So it leads to bigger errors. And so you can have just bad results, things that were wrong. It's not that inverse theory only applies to math and physics. I mean, we use it in our daily life all the time, and we don't even think about it. I mean, we're always making observations about the world around us, either personally or socially or politically or relationship-wise or whatever. And we actually have some knowledge about the world and how we think it works, which is generally incomplete, quite often wrong. But based on that, we put those two things together, and we figure out the causes of why we saw those observations, which is quite often wrong. I often use the example for those of you that have parents with teenage kids or something. Your observation is they were supposed to be home at midnight, because that was the time, and they were supposed to call you on their cell phone if they were going to be late. It's now 2 a.m., they haven't called, and when you call the cell phone, you get no answer. Those are the observations. What are the causes? Well, there could be a lot. There could be a lot of causes. One cause could be that the kid's having too much fun, the cell phone ran out of juice because they forgot to charge it, and they're just ignoring you. The other cause could be that they got grabbed off the street by some horrible person and you'll never see them again. The cell phone's been smashed to bits and is in the ditch. Two causes. One's probably more plausible than the other. You have to put some type of a priori constraint to pick one of those as the solution, and most of us pick the worst possible outcome we could think of. Oh my God, the kid's dead, we'll never see him again. And that's generally wrong. So that's an application of how you can use inverse theory in the wrong way. And if there's a way to change that so you just quietly relax and said, I just know that they're going to be home on time, okay, it'll be okay. Another interesting way to look at it is, you wouldn't think that it would be in literature, but I read all the Sherlock Holmes things when I was a kid, probably destroyed me forever, but he actually just used inverse theory. In the very first book, there's a quote from The Study in Scarlet, which Holmes is trying to explain what he does. Most people, if you describe a train of events to them, will tell you what the result would be. They can put those events together in their minds and argue from them that something will come to pass. Forward modeling. There are a few people, however, if you told them a result, would be able to evolve from their own inner consciousness what the steps were that led up to that result, the causes. Inverse theory. So it's everywhere. It's just that in our world, we try to put it on a sound mathematical basis, because that's what we do. So here's the example of ionospheric tomography. Here's your forward model. Given a 3D distribution of electron density, and if we know the geometry between a ground GPS receiver and a ground GPS transmitter, we can predict what the total electron content will be. Nice and simple. The inverse tomography, now I'm going to do the ideal mathematical sense and then the real one. So the ideal means that we have lines of sight of TEC from every possible angle and direction we can matter, that we can measure throughout the entire volume we're interested in, and the receivers and transmitters are outside the volume. We have continuous coverage at all angles. The TEC data is known exactly with no measurement errors. And from that, we can, from this integral relationship and an application of inverse integral theory, we can exactly and uniquely recover the electron density distribution from that. Well, the real world is we never have a complete set of data. We always have limited angles. It is impossible to get horizontal rays through the ionosphere, or even occultations go down and come back up. We never have receivers where we want them over the entire world. The data always has errors. We don't know the receiver biases to better than a few tech units. So our solution is not unique. It can have large errors. And in order to make it unique, we always need some type of a priori or other information, which in the best of all worlds is plausible physics, to come up with the electron density should be. Here's just a cartoon of your satellites. This is back in the day. So, I mean, we're just doing this in 2 dimensions. It's really 3 dimensions, but you can imagine if you had a bunch of satellites in a 2-dimensional thing and a bunch of ground receivers, you're getting all these rays. You'll notice there's no horizontal rays. It's somewhat limited here. But what you'd like to do is to recover that ionosphere if you could. And so you'd start with your forward model. Your measured TEC is going to be an integral from the receiver to the satellite of the electron density along the path. We'd like to pixelize this, so we'll break this density into a volume of pixels, and each of these will have a length through the pixel, and this will be an unknown density, and then this is your measurement as a sum, and there's, of course, an error now that we've done this. That's called a representation error. We can make that into a matrix, and now we've got it. If we've given the measurement with errors, can we determine X? And there's a lot of methods. This is back in the days of 2D tomography, pre all these fancy maximum likelihood using error covariance methods, where we tried to do this. And you generally started with some model of the ionosphere, IRI or something, and then you did iterative things. Probably the one that was most well known was the algebraic reconstruction technique. All of these are kind of outdated now, but that's what was done. Here's some of the others. And this is, you just updated each density iteratively based on the previous guess, which starts off with a model. You have some weighting factor here that you can change a little bit. And this is the difference between the data and the prediction divided by the length through all the volume of the pixels. And it works. It leaves artifacts. If you don't have good data everywhere, you'll see a line between you, the ground receiver, and the satellite, and it'll look like you've got a line of plasma along there, and you might get really excited about discovering something that is a nice discovery of an artifact, but it does work. And this is from Catherine Mitchell at the University of Bath. As far as I know, this is the first actual comparison of a tomographic image with an ISCAT at the same time and place up at Tromsø. This was presented at the 1994 Beacon Symposium, and it pretty much blew us all away. This is the reconstructed electron density image they got, and this is from when they were at the University of Wales at Aberystwyth. And this is what the ISCAT radar saw. And it's really, I won't go into it, but it's an amazingly good, the more you look at it, match. So it showed what we could do with the old transit 2D tomography things long ago. But the 2D transits, they just were regional, they didn't come all the time. So you really want to talk about, can you do 3D time evolving global images of electron density? And I'm going to talk a little bit about my algorithm, Ionospheric data assimilation 4-dimensional, which is a data assimilative algorithm, but it really started off years ago as an imaging algorithm. The things in red are some of the things that are kind of unique about it, as opposed to some of the others that have been here. I solved for the log of the electron density. That's nice in 2 ways. One is it guarantees positivity on the densities, and 2, in general, observational errors that we see of density and things like that are more log normal than normal. Part of that's just because the density is positive definite. It also forces the algorithm to be nonlinear, which allows it to be easier to take in nonlinear data sets, and also adds all the problems about nonlinearities that were mentioned before. My code has always been defined to be research-oriented, not operational, so I have users can select almost anything. You can put irregular horizontal grid, you can lay down 10,000 pixels in the United States if you want, and none anywhere else. And you have an array going up. You can configure the error covariance however you want. So that's kind of an overview of my algorithm. These are some of the data sources it takes, a lot of linear data sources, pretty much anything I can get my hands on, and quite a few nonlinear data sources, but I will say that pretty much in general, digisons are about the only thing I use regularly. I mean, I just have trouble getting bistatic HF time delays and things, so I don't get them very often. Whoops. So here's some results. This is science. This is the November 20th superstorm from 2003. How much time do I got? Okay. And this is looking over the US. There's the United States at different heights, 200, 300, 400, or 350, 400, 600 kilometers altitude. And this is the distribution of electron density. This is partially to show you that it's not just TEC. We get the height resolved electron density. And this is just as the storm-enhanced density feature at 17 UT formed over the eastern US for that day. And you can see here's all the really high density stuff at lower latitudes. Here's a bulge of it going right up here, along here. This is where this low latitude bulge of electron density forms right at the start. And you can see that it's the only place where it's extended in altitude. Something is lifting it up. And then it eventually goes on and becomes a plume, which I won't go into that anymore, but trying to understand the physics that cause that particular altitude distribution in that location is one of the things we've been doing scientifically. Recently, we've put in a lot more GPS receivers in Antarctica, and we've started to do imaging over Antarctica, and hopefully we'll do conjugate imaging with the Arctic. And this is from the first post-solar minimum storm minors it was, April 5th, 2010, and this is at 17 UT over Antarctica. I have this rotated, so I think noon is at the top, roughly local noon. And what you're seeing is this is the low latitude ionospheric density. There's a depletion region here. It's in the daylight. It's kind of hard to understand why it's there. And then we have this patch, or maybe it's an enhanced plasma of low energy flux coming in, precipitation, and this depletion region here, which is actually fairly near the anomalous low density region that I can't think of the name. Wendell C, thank you, region. And it turns out we had a lot of scintillations with this. This is just an image. And here is a plasmaspheric image. So we can use this and extend it up through the plasmasphere and use LEO satellites from COSMIC looking upwards. And what I want to do is I looked at 10 days in January of 2009, and because there is this kind of winter anomaly, ionospheric effect over the US sector, I wanted to see if it was maybe coming from the plasmasphere. So if you look at the US, you'll see there is this extended, quite often, region of plasmaspheric densities going out to an L shell of 4 that's associated with the kind of Western Hemisphere sector. So that's just an example of something we're looking at in terms of trying to understand plasmaspheric imaging from. Yeah, that's tomography. Yeah. Of course, all we're doing is looking at electron density at this point, and electron density is kind of the tail. It's not the dog wagging it. It's the drivers are energy and momentum, so that means temperatures, winds, E cross B drifts. And those are much harder to measure and to get at. So a few years ago, we wondered, could you take this organized 3D time-evolving maps of electron density and somehow, using, again, inverse theory, figure out what the drivers had to be that caused it? Because, from the electron continuity equation, it has to be something that caused it. So we developed at Astra a method which we call Empire, and what we do is we take all these densities and we use the continuity equation and we turn this into a linear estimation problem. We expand the unknown fields and winds in low density power series, and since I'm near the end, this is our match against the incoherent upper Millstone Hill radar for the November 20th storm. We did quite good, and I won't go into it, but we did show that for this case, people think the uplift is generally due to the E cross B term, and in this case, it was actually more due to field-aligned drifts, which probably means winds for this November 20th, and we're still looking at that. Where I hope to go with this is I hope to bring in Empire as an estimator and have a continuity equation forward model, and then have this as being a a full forward prediction physics-based data assimilation model, and that's basically it with summary.